Hi everybody, welcome back. I'm going to open up with a little brain teaser physics question. So you know Newton's third law of force pairs that we were talking about? Why don't force pairs cancel out? If all forces come in pairs that are equal and opposite, how does anything happen? Okay, so imagine a game of tug of war. We have a rope with this little flag in the middle so that we can clearly see where it's going. There are people on the left and right ends of this rope. They say, 1, 2, 3, go. And only the person on the right pulls. Can you predict what's going to happen to that little flag in the middle? Let's take this further. Say that we, the audience, have some sort of blinders and we can only see the flag in the middle. We can't see the person on either side or what they're doing. So we hear them say 1, 2, 3, go. And we see the flag creep over to the left. Without even seeing the people on either side, what can we conclude about the strength with which they're pulling? We can make a comparison and say that the left side is pulling stronger than the right. Okay, so now say they reset the rope. They say 1, 2, 3, go. And suddenly the flag goes flying over to the left. What can we conclude about the forces now? Is this different than the previous case? Now, we know that a force is caused by an interaction between two objects, but that an object can interact with more than one other object at the same time. Think about the rope. It's interacting with the person on the left, and it's also interacting with the person on the right. So what happens when there's more than one force acting on a given object? Just from what you know about tug of war, you can probably tell intuitively that when more than one forces act on an object, we can find their total by adding them in a way. Remembering, though, that force is described with both a magnitude or strength and a direction. So we need to think about both of those factors and add all of these things together. It's different from just adding plain numbers. So what does it look like? I'm going to show you a really simple way to represent the forces acting on an object. To represent the object, I'm just going to draw a dot. I want to keep these diagrams as clean and simple as I possibly can. Then I'll draw an arrow to represent each force acting on the object. Remember, the length of the arrow represents the strength of the force, and the direction just represents the direction. So, for example, this shows a force acting on the object to the right. This shows a little baby force acting on the object to the left. Let's return to the example of tug of war, and instead of showing the whole rope or the flag, I'm just going to use a point to mark the rope's center, and we'll use arrows to represent forces acting on the rope. Say at first the rope is still, and then suddenly just the person on the right starts pulling. We know that that's going to make the rope start moving to the right. So what if there's more than one force acting on the rope? Now say we steady the rope, reset it, and then say 3, 2, 1, go. And now the person on the right and the person on the left pull on the rope with equal strength. What happens? The forces balance each other out, and the rope doesn't move. Reset. The rope is still. We say 3, 2, 1, go. Both people start pulling, but this time the person on the left is pulling a little bit harder. What's the rope gonna do? Picture it in your mind. Now imagine we reset. Steady the rope. We say 3, 2, 1, go. And both people pull, but the person on the left goes absolute beast mode and pulls way harder than the person on the right. What's going to happen now? Is this the same as in the previous example when the person on the left pulled just a little bit harder than the person on the right? Well, in both cases, there are forces of unequal strengths acting in opposite directions. But we have to consider just how unequal are the forces. Let's think about this using our arrows in the diagram. Remember, the direction of an arrow simply represents the direction of the force. The length of the arrow represents the force's strength. So here, where old Lefty is pulling just a bit harder, there's a small difference between the arrow's lengths, which means that there's a relatively small, unbalanced force to the left. But here, where Lefty is going all out and pulling way harder, there's a much more significant difference between the strengths. So there's a much greater unbalanced force to the left. Because of this, we're going to see a much more significant reaction by the rope moving over to the left much more rapidly. What we've been talking about, finding the total force along these directions, is called finding the net force, where net just means total, or like a mathematical sum. In this case, we identify the force acting on the rope to the right and the force acting on the rope to the left, and then we add them, we compare them, to see if we end up with a total or net force in either direction. We've seen that a net force to the left causes the rope to start moving to the left, and a net force to the right causes the rope to start moving to the right. But what about when the left-right forces balance? Okay, back to our thought experiment. What if they reset the rope? We can still only see the flag. We hear them say, 3, 2, 1, go, and the flag doesn't move. What can we say about the relative strengths of the forces now? It makes sense that the forces are equal. They're balanced, since the flag hasn't started moving in either direction. But what can we conclude about what the actual strength of the force is that they're applying? Say we ask the person next to us, and they say, well, the flag isn't moving, so we know that they must not be pulling. Do you agree? Can we tell if both people are pulling gently, or both pulling hard, or not pulling at all, just by seeing that the flag doesn't move? Well, we know that the net force can equal 0, but 0 net force does not mean that there are no forces acting at all. We can think about the simple case of an object that's just resting on a surface, say this book on the table. The book's motion isn't changing, it's just sitting there in one place. So it's safe to say that there is 0 net force acting on the book. But does that mean that there are no forces acting on the book? Can you name any? Well, the book is here on Earth. The book has weight. So there's the force of gravity due to Earth pulling the book down. But the book isn't falling down. Its motion isn't changing. So there must be some other force acting in the opposite direction to balance that force out. The table is here to hold the book up. It's exerting an upward force on the book. So we've identified an upward and downward force acting on the book. We know that their strengths must be equal since they sum to 0. Remember, gravity doesn't just switch on and off. It's always pulling the book downward. And what happens if we remove the force of the table then? This. We get an unbalanced force, a net force in the downward direction, which makes the book fall. It starts moving downward. Okay, so we've seen that when the book is just chilling on a surface, like the table or the floor, there's a downward force acting on it and an upward force acting on it. These forces acting on the book balance because they're equal in strength and opposite in direction. We've seen how we can use arrows to represent this, and it seems to make sense. A certain amount up plus the same amount down balances out to 0. But wait, equal and opposite. We've heard this before, right? Aren't we just talking about Newton's third law? Isn't this just a third law force pair? You tell me. The forces are the force of Earth's gravity acting on the book and the force of the table acting on the book. Think carefully about the number of objects that are involved here. We have the book, of course, and we have its interaction with Earth, and we also have its interaction with the table. That's 3 objects. Let me repeat Newton's third law. If A exerts a force on B, B exerts a force on A that's equal in strength and opposite in direction. That's 2 objects. Where does a third object come into play then? When in doubt, we can take a step back and think about our definition of force, an interaction between 2 objects. So for one, we have an interaction between the book and Earth, the gravitational force of Earth on the book. Applying Newton's third law to identify the third law force pair, we just switch the 2 agents. We get that the other force in this pair is the gravitational force of the book on Earth. Remember, any 2 objects with mass are gravitationally attracted to each other. Boom, that's a force pair. Now we can think about the interaction between the book and the table. There's the force of the table acting on the book. Applying Newton's third law, we know that the other force in this force pair is the force of the book on the table. If you've been counting along at home, you might notice that we just identified 4 different forces. So why would the force diagram for the book only show 2 forces? Well, a force diagram like this is used to analyze the forces acting on a single object, in this case, the book. That's why we see the force of Earth on the book and the force of the table on the book. These are the forces we add together. When we find the net force, we're finding the total force acting on a given object. Now, returning to the question I asked at the very start of this video, And it's a fair and really common question. A lot of people ask, if all forces exist in pairs that are equal and opposite, why don't they all balance each other out and give a net force of 0? How does anything at all happen if all forces are instantly just balanced to 0? Well, they're not. It's because by definition, a third law force pair, or just force pair, describes the interaction between two objects, A on B and B on A. We don't find the sum of these forces because they're acting on two separate objects. Anytime we do want to find the net force on an object, we add together the forces that are acting on that one object. Shifting gears now, let's get a little bit more practice with finding the net force on a given object. Of course, there can be more than one force acting on an object in a single direction. Like say, if you and your friend worked together to push a heavy box across the floor. There's one force in a direction and another force in the same direction. To find the net force acting on the box, we just add these forces together and see that the net force is one big force acting in that direction. So far, we've seen a bunch of examples of adding forces that act in the left-right directions. But of course, there's more than just left and right. An object can be acted upon by many forces in many different directions. Say we have an object that has these forces acting on it. There's a force in the upward direction and a weaker force in the downward direction. And there's a force to the right and a weaker force to the left. How can we find the net force? Well, we've seen how to do this for the left-right case, and it's the same deal for up-down. When we have perpendicular forces like this, we can analyze the up-down and left-right contributions separately. Let's start with left-right. Comparing the left and right forces, we see that the force to the right is greater than the force to the left. So along that direction, there will be a net force to the right. Now for up-down, the upward force is greater than the downward force. So there's a net force in the upward direction. So our force diagram has been simplified to find the net force in the left-right direction and the net force in the up-down direction. Can you think of any ways to simplify this further? Here's a hint. Say you want to go sailing or whatever, so you check out the wind forecast. You find out that the wind is blowing a little bit to the north and it's blowing a little bit to the east. Can you think of a way to represent this as wind that's blowing in a single direction? Northeast, right? There's some north, there's some east, it's northeast. Same kind of deal here. We take contributions from perpendicular directions, like north and east or up and right, and combine them into one total. So the net force, or the total force acting on this object, shown here in blue, points up and to the right. It actually adds very simply. We take the upward contribution and the rightward contribution, and we get a force that points up by that same amount and to the right by that same amount. So, to summarize, we saw that when more than one force acts on a given object, we add all the forces acting on that object to find the net or total force. We saw again why the two forces in a Newton's third law force pair don't balance to 0. In order to find a net force, like to see if any forces do balance, we look at all the forces that are acting on a single given object and then add up their contributions. We'll see in the next lesson why that resulting net force is so significant. See you then.